As Chris said, I'm very friendly.
Should we also minimize the dark window?
Yes.
Oh,
What about the overhead light? Do you want to kill that?
should we kill that as well? Yeah.
There's several of them that all deserve.
I don't know. There we go.
There's that light that goes like this.
Okay. Are we good to go?
There's some sound from the end.
Yeah. I can do that. I think that works. Yeah.
Perfect.
Cool. Awesome. Yeah, thank you so much for having me here. I will be around for 2 more days, so you're welcome to just pop by and have a chat. I don't have so much pre-planned for the next few days. But so as Chris mentioned, I'm Martin Ray. I'm a Beecroft Fellow at the University of Oxford. And today I wanted to talk to you about some work we've been doing on understanding the diversity of stellar halos around Milky-Way galaxies. And I thought I would start by a pretty basic reminder that galaxies come in all sorts of shapes, forms, and sizes. So here you have these great pictures from the Hubble Space Telescopes of blue galaxies that are forming stars, and on the right, an elliptical red-looking galaxies. And you can extend this diversity to all sorts of galaxies, really, including some of my favorite objects, these dwarf galaxies down there, which barely look like anything, especially on this projector. So this is really the whole premise of this talk. The goal that I've been pursuing in recent years is to really try to understand how does the diversity of galaxies come to be in our universe. And when we start to answer this question, there's a very obvious difference between all these objects, and that's simply their mass. So the dwarf galaxies is tiny, whereas the elliptical is massive. And it's become very clear in recent years that one of the main things that regulates galaxy formation and drives the diversity of galaxies is simply the halo mass. That is the depth of the potential well in which galaxy exists. And that's basically because that defines how much gas they can entrap from their cosmological surroundings, and eventually how efficiently they can turn it into stars to grow their stellar content. And so here I'm just showing you what's called the abundance matching relation, where that relates the stellar mass of galaxies, or the efficiency at which they're forming stars, to their halo masses. And there's, if we put back the 3 pictures I was just showing you, typically dwarf galaxies live in small dark matter halos towards this halo mass end here. This galaxy lives around the Milky Way scale, around 10 to the 12, and elliptical galaxies tend to live in the most massive halos in the universe. So at this point, we've kind of answered the question, right? We've like, okay, what drives the diversity of galaxies? Well, it's mass. Primarily, to a very good approximation, the primary driver is mass. There's several things worth noting from this plot. The first one is, I don't know if you noticed, but there is this wildly discrepant predictions at the low mass end. And I've done a lot of work on understanding the diversity of the dwarf galaxy population, and you're welcome to come and ask me about it. Because today I actually want to focus around Milky Way mass objects. And that's because even though the predictions actually converge reasonably well around the Milky Way scale, there's still significant scatter at any given mass. And this scatter at fixed halo mass, we expect scatter in stellar mass, and there's now many lines of evidence that this scatter is correlated with other secondary galaxy properties.
When you say predictions, what do you mean?
As in,
those different lines, what are the different lines?
There are different ways of mapping dark matter halos, the stellar mass of galaxies onto their dark matter halos. Different models.
So in every case, it's somehow using data and interpreting it differently, like to decide which is it that's getting decided, the halo mass is being inferred, or what? I'm just interested to.
So you can do this mapping in different ways, but typically what gets done is you take the abundance of dark matter halo across the universe, and then you map it onto the abundance of stellar mass, the stellar mass function across the universe. But the way, there's a bit of devils in the details in the way you make this one-to-one mapping, or not so one-to-one, so that you can allow for scatter.
But it's at least a half the deck, and in some parts a whole.
That's right. And part of this scatter is intrinsic, as in we know that okay, so I can show you the next plot I was going to show, which is this great study from Lorenzo Prosti, where you can use local galaxies for which you have really detailed rotation curve in the case of disks, or a population of globular cluster from which you can infer dynamics and dynamical masses. And from that, you can infer individual halo masses. And so these are the data points that you see here, the halo mass to stellar mass relation. And one of the things that was quite apparent from this study is that at a given halo mass, the disks tend to live towards the upper part of the scatter compared to the elliptical towards the bottom part. And in gray is one of this abundance matching model, one of this line that you see here in the background, which is really the average relation between the two. And this is how you get the average, but the scatter and where you are in the scatter seems to be correlated with secondary galaxy properties. Does that answer your question? Yeah. Okay, so there's clearly a lot more information than just mass. We haven't really solved this problem, and the reason we haven't really solved it is because, well, galaxy formation is actually really hard. And here I'm just re-showing you the same movie as the beginning, and okay, it's a bit jaggy on Zoom. But the bottom line is that galaxy formation is a highly dynamical process that is, so here we're following the gas density as the galaxy assembles over the entirety of cosmic time. And you can see this filamentary structure coming from the cosmic web that is feeding the galaxy its gas. You can see these merger events that eventually throw galaxy together and trigger different responses. And if you look carefully, you'll see this explosion, these expulsions of gas coming from the center of the galaxy. And so that's really what's difficult about galaxy, is that they intertwine really large cosmological scales with really small scale, highly nonlinear astrophysics within them, the physics of stars, the physics of black holes, that is capable of ejecting gas all the way back onto this cosmological scale. So we really have a huge dynamic range that is highly nonlinear. We need to solve hydrodynamics, we potentially need to solve MHD, radiative transfer. It's all basically a bit of a mess. So it's almost a miracle that we can explain so much about galaxies just based on their mass. And so that puts us in a slightly awkward spot, like where, as many places in astrophysics, we constantly have to make this trade-off between volume and resolution when we try to model observations of galaxies. And there's several ways to do that. There's several ways to do that and several trade-offs that you can do. One of them is to use what we call cosmological boxes. And the best example, maybe you've heard of it, is, Illustris TNG should be behind my screen. And so the idea here is you just take a chunk of the universe and then you do your best guess at what the astrophysics is doing. And by comparison, you have pretty low resolution because you're simulating a very large number of objects. At the other end of the spectrum, we have idealized setup of galaxy formation, where we basically have galaxies in a vacuum. And here we can afford a lot of resolution because by construction, we're getting rid of all these filamentary structures and accretion patterns. And so today I'm going to be mostly talking about an intermediate technique that's called zooms. And the idea is that you keep the full cosmological box, but you evolve it at low resolution. And then you concentrate all your efforts into this one specific region that is going to form one object. And so you're really trying to bridge the gap between these two techniques, where you still have this feeding, the filaments, all the mergers, but you're also putting in a lot of effort in resolving the internal astrophysics of this object. So this is great. Zooms are really, really important techniques. They've been a really important technique in the literature. And this is all the movies you've seen have been state-of-the-art cosmological zoom simulations of galaxies. The problem is, even if we could do that, and even if we had the best knowledge of all the astrophysics, we would still be at a standstill. And that's because here are two objects, two movies of two galaxies that assemble the same halo mass. And I've said halo mass is the main driver of things. However, they have completely different environment and completely different way this mass is accreted over time. And what we really want to be able to do is to say, this galaxy on the left is going to form a disk and be star forming at redshift 0. And this galaxy on the right is going to form an elliptical and be quenched on redshift 0. And I dare you to tell me, looking at this, which one is going to be which. And that's because, as I've said, galaxy formation is a highly nonlinear and complex process, but on top of that, in a lambda CDM universe, there's a large diversity of possible ways each galaxy can assemble itself. And each of these formation scenario couples to the nonlinear astrophysics to produce the scatter that we observe in the galaxy properties. And so we are still really far from answering the question of how do we causally interpret galaxy formation observation? How do we distinguish different scenarios? Can we even hope to disentangle them from their astrophysical uncertainties that we might have in stellar evolution or in black hole physics, for example? And this is really the type of question I'm going to try to not answer, because you can never really answer anything, but get better at today.
You say that lambda CDM universe generates diversity. Would it be different if it was just a CDM universe?
It's not really, okay, so maybe this should be a bit more precise. It's really about inflationary perturbations growing under gravity. So it doesn't really depend on whether W is -1 or 1.1.
It's the CDM
yes.
part, is it?
Yes.
Okay.
So it's really about more the
No, I was just,
yeah.
That's what I thought.
Yeah.
But if this was a window onto this question of why now, that would be really cool.
Agreed. And I think the problem, it could be if we had this part, the nonlinear astrophysics, under control, and we really don't. And it's one of the main uncertainty that we have. Okay, so I'm going to try to convince you that, so there's many ways to go at this question, and I'm going to try to convince you that one really interesting one is to look into the stellar halos that surround these galaxies, and what we can learn from the faint outskirts around these objects. And so here I'm showing you the same movies as before, but now looking at the stellar component. And you can see the central galaxy in the center here, and you see that there's this kind of diffuse body of stars that surrounds it. And you see that as other objects merge with it, so I'm sorry, it's very jaggy. As other objects merge with it, you see this kind of plumes of material that gets stripped from the different mergers. These very distinct streams and shell patterns that form around the galaxy. And basically, all this halo of stars, this diffuse halo of stars, encodes an enormous amount of information about the past history of the galaxy, in particular because the dynamical times are very long. So there's a lot of memory that stays in the halo compared to the center galaxy.
And so how big is this halo relative to the
it's almost, it can be as big as the dark matter halo. And I will come really quickly into why it's so difficult to actually see it. And that's because it's so big and diffuse. But just quickly for now, the idea is that you can hope, if you could observe it, you can hope to learn about all these past interactions and the history of the galaxy. And I'm just going to skip this now. And as you said, there's a massive but to this question, and the but is that they are extremely diffuse structures and faint, and so observationally they're really, really tricky to observe. And the best way to see this is an image of the galaxy we're looking at around the surface brightness of an SDSS image. And you don't really see this whole diffuse component around it. Whereas if we allow ourselves, and now I'm cheating because this is simulation data, if we allow ourselves to go down 2 orders of magnitude in surface brightness, you might be able to see some glow starting to appear around the galaxy. And actually, if we push this, then you start seeing this really faint glow that makes up the stellar halo.
Wouldn't this also just be a lot easier with an edge-on system?
They have some shape to them, but they are mostly spherical. And that's almost...
No, sorry, I meant if the actual disk of the galaxy was edge-on. I thought you were looking, oh, we're just looking at the diffuse halo. Okay.
That's right.
Okay.
Yeah. So it's really like a kind of phase mixed structure around the galaxy. So they carry some shape, but they kind of pretty blobby. And yeah, and so for the longest time, the only real stellar halo we knew around this galaxy was actually just the one of our Milky Way. And that's because in the case of a Milky Way, we actually sit within the galaxy and we can count individual stars that make up this diffuse component. And so here I'm showing you the stellar mass of a galaxy and the amount of halo of stellar mass in the halo. And as I said, this is where the Milky Way sits. And as you're probably aware, there's been the Gaia satellite really recently. And so for each of these individual stars, we can now make a lot of, we have enormous phase space and chemistry information that we can hope to use to unravel the Milky Way's history. And I'll come back to this point toward the end of the talk, because for now I really want to take a diversity and extragalactic focus. And that's because there's been a revolution in the last decade in the quality of photometric imaging at low surface brightness. And this was primarily driven by the Dragonfly telescope here, but also some of other cameras and some dedicated program on HST. And what happened is we went from this one data point in until 2016 to suddenly basically a sample. It's a sample of 15, but it's a sample nonetheless. And what became really quickly very apparent is that this sample at a given stellar mass exhibited a really strong diversity of stellar halos around similarly looking disk galaxies. And when we started comparing these predictions against our best models for cosmological galaxy formation, this is what happened. So here I'm showing you some results from the Artemis Zoom simulations, some results from the Industries TNG simulations, and some results from the Auriga simulations. And my goal here is really not to point fingers. It's really a way to say that there is a lot to be learned about our galaxy formation modeling in the fact that our models really struggle to explain this diversity of stellar halo. And actually, most of these comparisons were done by the people doing the observation in 2016 and 2017 that then went on for to use simulation data.
So are these observational points, are they from different surveys, like different telescopes, each of them, or is this just like one telescope?
So so 6 or 7 of them are from the Dragonfly telescope. 5 or 6 of them are from dedicated program on HST. And then 2 of them are individual studies with, say, CFHT cameras and so on.
Cool. Okay.
So they are slightly heterogeneous sample.
Just to be sure I understand the vertical axis, so in every case you count stars, or the massed stars, and in one case that you use it, the horizontal axis is the total stellar mass, which is the disk plus the halo, and vertically it's just the halo?
That's right. And again, it's a slightly heterogeneous sample in the sense that some of them are made by converting the surface brightness profile to a stellar mass. Some of them are made with HST, where you actually resolve each individual star in extragalactic halo. And then what they do is they take a disk and then they make a pointing like this, or several pointings along an axis to derive a number count profile that you turn into a stellar mass. So there are subtleties in making these comparisons, and there's a great paper from Robin Sanderson that looks into this in detail. The details that they're not really details, but they don't explain everything. And in particular, I recommend reading Alison Merritt's 2020 paper, where they analyze Illustris TNG with exactly the same pipeline as the Dragonfly telescope to basically show that there is too much mass in the outskirts of galaxies with current cosmological simulations. Okay, so what I really want you to take home from this is that we are now at a point where we can make samples of extragalactic stellar halos, and this is really only going to get better because the cameras only really improve. And in particular with Vera Rubin and Euclid, we're going to get even more resolved star stellar halos and low surface brightness images.
Are these like selected to not be in groups or anything like that?
They are isolated disk galaxies. So the only real selection is that they are nearby, because you need to be able to do low surface brightness imaging, isolated massive disk galaxies that kind of allow us to put that resemble enough the Milky Way that we might be able to use them to put context on the Milky Way.
And is mass to light ratio an issue? I guess not, because you're just comparing stars with stars. but you might think that the ones that were on the outskirts were a different, more difficult to see population, maybe. Oh, but that goes the wrong.
I think it goes the wrong way because you become more and more dark matter dominated. So I think the mass to light ratio will change with radius.
Right, because you might think, well, I was thinking, I may be making something up that's wrong, but I was thinking that older stars would, seems to me, naturally have a lower light to mass ratio.
Yes.
And those would be typically further away.
That's right.
And therefore they would be harder to see.
Right.
And so you might observationally underestimate them unless you understood how to do that correction.
Yeah, I don't know the answer to that. I think, so they are older stars, like the halo is made of old stars.
Right, and so you'd have to make some adjustment for the likelihood of observing the star based on some model of their.
Yes, I think so. Yeah, I don't know the details of the observation that much, or of that detail specifically. Yeah. Any other points on this, or no? Okay, so yeah, so this puts us at it's a great opportunity to both constrain the histories of this galaxy through the amount of mass that they have in the halos and potentially the streams and shells that they might exhibit, and constrain our models of galaxy formation, providing we can interpret these observations. And again, this is not meant as a negative comment. It's really a testament of how difficult the problem is, and that's because we, as I've said, we constantly have to trade off between volume and resolution, but stellar halos are, by construction, cosmological features that form from the accretion and the mergers of many building blocks over the history of the galaxies, while at the same time being the progenitors of them are really tiny dwarf galaxies that get disrupted and require a lot of resolution. But on top of that, there's a third axis to this plot that we don't think about too much and too often, because you might think, well, then that's great. We can use zoom simulations, which are perfectly suited for these types of tasks. But there's a third axis that I will call control. And the idea of it is that when we have idealized simulations, we have full control of our initial conditions. And what I mean by that is I can take two galaxies, throw them together head on, observe the final halo. I can take two galaxies, throw them with some angular momentum, observe the final halo, and then make a comparison and hope to make a causal argument that says this is how the different types of mergers influence the final halo. When we look at cosmological simulations, what really happens is everything starts as random perturbations. And this is all inflationary stuff that has been inflated to cosmological scale. And if I take a second object that has the same mass, its initial condition looks completely different. It will sit in a different cosmological environment. All the mergers will be seeded a different way. And so it's actually really difficult to compare them and to relate the final product you get to the merger history, because everything's changed between each of these objects. And so one of the points I want you to take away here is that this is what I'm going to try to do. And this is not a Brexit joke, it's taking back control into, yeah, you're probably the only one who really gets that. But it's taking back control and putting it back in a cosmological setup so that we can do these comparative, more causal experiments with stellar halos. And the way I'm going to do it is with a technique called genetic modifications. And the idea of it is that you start from a given initial condition that gives you a specific object with a merger history. And rather than picking something that's completely different and randomly different, you actually construct a new initial condition that looks almost virtually the same. And the point here is that it's almost exactly the same so that you can eventually compare them together, except that within the patch that will be the galaxy, you engineer the original density field to make specific changes into the galaxy. And so when you produce the two movies, you might have the feeling that these are quite hard to distinguish visually. And this is, again, this is the point. They have the same environment and they're very, very similar looking objects. But if here I've engineered the initial conditions, the cosmological initial conditions of these two objects such that these three mergers here are systematically brought earlier at the same when we pose the movie at the same time, the 3 mergers are made earlier in the bright object. And I'm not going to go into there's an extensive mathematical background on how we achieve these changes and how we actually implement them. And I'm very happy to answer questions because I would like to focus on results today. But yeah, so to put this in a more quantitative way, this is the halo mass growth of the 2 objects we were looking at as a function of time. And what's really important here is that this is a very controlled setup where these 2 objects have the same early growth, they have the same late growth, and they assemble to the same total mass. They have very similar large-scale cosmological environment, but they have this change in how quickly the mergers happen at redshift 1.5. And actually, one of the key aspects of this idea is that you don't need to stop there. You can actually push it a little further, take the same mergers, make them even earlier, or actually turn the tune the other way, and take these mergers and make them even later. And so really, when we start doing this, we're introducing targeted control changes while being in a cosmological environment and keeping all the other variables untouched, in particular mass and environment. And okay, so far this is a purely kind of dark matter idea, and we still need to build stellar halos out of this. And so here, in order to maximize our capability of exploration, I'm going to use a semi-numerical technique to build stellar halos. I'm going to take a dark matter merger tree that you see here, and then paint the stars onto it using an analytical, empirically calibrated model from eMERGE, called eMERGE. And again, I'm happy to discuss the details of how we do this if you wish. And that will tell us how many stars are in each progenitor galaxies that will end up in the halo. And then we also need to know where do the stars end up when they become disrupted and form the final object. And so for this, we use an approximation called particle tagging that assumes that stars form at the bottom of the potential well, and that the kinematics of stars end up being well represented by the kinematics of dark matter. So here, the core assumption is really that dark matter simulations are enough to predict how things are being disrupted in the host potential well. And there are limitations to that, and I'm happy to answer questions about it. Because once we've done this, we can actually construct stellar halos for these different merger scenarios and actually compare them with one another. And immediately when we did that, what we realized was it was very, very striking. So here I'm just showing you a stellar density map of the brown scenario on the left and of the pink scenario on the right. And you can immediately see that one of them is incredibly more massive.
Sorry, is this at the final snapshot, or is it?
That's right.
Okay.
This is the halos at redshift 0. So again, they have the same early growth, same late growth, and you're just comparing at redshift 0 the difference that the changes in the history have made. And so to put this in a more quantitative way, this is the stellar density profile as a function of radius. And if I define the halo as just being a anything that's outside 20 kpc, which is well outside the central galaxy, and if you map the colors from left to right in your head, you should see that there's a very systematic effect, and that the later I make this major merger happen, the systematically brighter the outskirts are, and with more stellar density.
So from your earlier slides compared to data, we learned that the cosmological simulations are doing it.
So we'll see what we learn. Because here I'm changing the merger history, and then there's this other axis that you can change, which is how much stellar mass is there in a given halo, where do you form galaxies, and how much stellar mass should they have in the first place, which contributes to the actual budget that you have to build a stellar halo with. But that's really the key. You're like jumping 5 slides, but that's really the key here.
It's a beautiful idea what you're doing,
right?
To sort of really use the knobs carefully.
But the idea is to actually put yourself in a position where you can hope to decouple these two problems, which is really what we're trying to achieve here. And so as you said, this is enough to generate about 1 dex of scatter in the stellar halo masses, which came as a bit of a surprise because here these are just one object with 5 different merger scenarios, and we're already generating really, really large diversity in the stellar halo context.
So this diversity will come from like a percentage change in the density field in the initial conditions.
That's right.
It's really small effect.
Yeah. And you can measure how big or small a change you're making from the initial conditions using by comparing the two density field with like a chi-square statistics. You can compute, it's Gaussian, so you can compute the difference in likelihood between each initial condition and try to relate it to how many degrees of freedom you might have.
It's actually fascinating because one might have incorrectly guessed the opposite, isn't it? That you get more stars if you somehow have less halo mass early.
That's right. So this came as a bit of a surprise, and one of the beautiful aspects of this is that because you're comparing things incrementally, you can hope to build trends between them. And that's what, so here, this is linking directly into what I wanted to show you here, where, so the total profile is this solid line that you were seeing just before, and this dashed line here is the accreted profile. And what you can see is that the accreted profile doesn't actually change that much between each of the different scenarios. But the total profile does. And here, this triangle here shows you where the accreted component starts dominating the outskirts compared to the in situ component. And there's a very systematic trend where as we make the major mergers happen later, the outskirts become in situ dominated even further and further out. And so the idea is that the later your major merger, the more material you can scatter from and shuffle from the inside galaxy and scatter on wide orbits that ends up in the halo. And so you make the stellar halo more massive, but also more in situ dominated. And so that's really, that's the type of more causal idea that you can get out of this approach. And as you were saying, one of the idea of doing this kind of flexible...
So that would mean though that should be the stellar disk stars kind of scattered out, so you would be able to see that in their ages, right, or something?
That's right. So we haven't actually done this, but my gut feeling is you should be able to see this in both metallicity and ages patterns. And the reason we haven't actually done this is it's not that easy to build an empirical model for metallicity and ages. The star formation history that you get out of empirical models are pretty coarse compared to what you might need to interpret ages data.
Even just in the Milky Way, we have data, right, of a lot of that. And I think there are some of the features that are thought to be puffed up disk material, but I didn't know that would contribute out to, this looks like the difference is all the way out to 100 kpc.
Yes. So this is very much, when you get to this pink line here, you're really at the edge of what's possible in terms of merger history in the lambda CDM universe. So you're pushing towards somewhat outlier in terms of the overall population. But I think the trend remains, as in like the comparative trend between the different scenarios holds, even if you might not actually form something like this. And the reason I'm saying this is that there is actually a lot of model uncertainties in what we're doing. And one of the points that we wanted to do was to explore how these uncertainties then propagate onto this diversity of the stellar halo.
And those were all for the same final stellar mass.
That's right. So this is same halo mass, same stellar mass, same environment, just different merger histories.
But the stars obviously were forming in the same. So I was wondering whether this was very sensitive to feedback, but I guess it's not, because...
I think it is to some extent, and I can show you at the end. I'm hoping to show you some examples where we do this with fully hydrodynamic simulations. And then you will see that some of the patterns don't really seem to depend so much on feedback, but actually...
Sorry, I was curious.
No, that's fine. So it's exactly what we're trying to understand, actually. Like how much of this depends on the details of feedback or the details of galaxy formation. And one of these details is, so here I'm showing you again the same plot of the amount of stellar mass in the outskirts, and this is the total mass in diamond, and the crosses are the accreted mass. But one of the uncertainty that we have is what's the budget that we can accrete in all the dwarf galaxies. So there's a lot of, I mentioned at the really beginning that the stellar mass to halo mass at the low mass end is very uncertain. And so that defines how much stellar mass is available for each dwarf galaxies that then gets disrupted in building the stellar halo. And so here I'm showing you our fiducial stellar mass to halo mass at the low mass end, and then another determination from the literature from Ethan Nadler, and then another determination from Justin Reed in 2017. And what I want you to take home is that at 10 to the 10, this is orders of magnitude in the different stellar mass that you can get for a given halo. And so that really potentially impacts how much material and budget you have to build the stellar halo. And
so do you mean of the accreted satellites?
Yes.
Okay.
Yeah.
Because then I can't figure that out, how that correlates with the previous plot where you showed that they were all kind of the same in stellar mass density. They were all contributing the same.
Yeah, so the previous plot is done with one model. Mm-hmm. And here I'm just going to add redoing the same previous plot and computing these masses with each of the three models, which is what this kind of efficient modeling really allows you to do. Okay. And what happens if you do that is you can see the crosses, the accreted component goes up.
Yeah.
And that makes sense because you're allowing each dwarf galaxy to yield more mass, basically. Yeah, so as you have shallower stellar mass to halo mass for dwarf galaxies, you build more massive halos that are increasingly accreted. Mm-hmm. But what was interesting is that the diversity that we saw generated by these differences in situ halos actually kind of goes down a lot. And that's because you're suddenly washing out the signature of the major mergers, scattering in situ stars, and overcoming it with all this extra accreted component. And okay, so at this point you might say, well, this is all well and good, but this is really like one object with one really merger scenarios. But we actually tested this in a completely different setup with a completely different objects, where we took unrelated object and picked a radial merger at redshift 2 that I then genetically engineered to make this specific merger smaller and larger. And once again, what we saw was that as you change the star formation histories for the dwarf galaxies, you would reduce the diversity. You would make more massive halos because they are more accreted, but you would reduce the diversity. And so getting the stellar mass to halo mass right for the dwarf seems to be an incredibly important component to getting the diversity of the stellar halos correct. And this is now a point that has been made a few times in the literature. And I think one of the avenues that we need to solve for cosmological simulations. Okay, so really what we're doing here is we are in a great position because we can now start to disentangle how different merger histories and different galaxy formation physics affect distinctly the diversity of stellar halos. And in the last kind of minutes of the talk, what I want to talk about is, can we invert this information and actually use it to reconstruct a galaxy's past history? And okay, so some of you that have heard of this might have realized already that this is not a totally randomly picked merger scenario. And that's because a radial merger at redshift 2 is exactly what we believe happened to our own Milky Way. And these are findings that came out of the Gaia data releases that saw debris in the halo of the Milky Way and inferred that it must have undergone a radial major merger at redshift 2. And so what we then wanted to do is to see if we could use these types of experiments to inform on the formation of the Milky Way and maybe learn how do this radial merger reproduce or don't galactic observables. And so in order to do that, you really need to model the galactic disk. And so you can't really rely on dark matter only simulations. And so what we did was to team up with Oscar Agates in Lund, and this is a slightly overwhelming site because everything's moving at the same time. But the point again is we took these 5 scenarios and redid them with state-of-the-art cosmological zoom simulations. And again, I can go into details of the ISM physics if you wish. They are here. They are very high resolution. They cost us a lot of CPU time. And the basic point once more is that these are really 5 times almost the same object. They form from the same filamentary structure. They have the same total mass, the same stellar mass. But if you look here, there is this merger around redshift 2, which is bigger here, much bigger here than it is here. And that's kind of what we are hoping to see as a progression as we turn the tune of this merger being bigger and bigger and bigger. And so this is very preliminary because we haven't actually fully analyzed all the simulations, but it's very exciting. So I'm going to share it anyway. And so here is what happens. This is what the final galaxy looks like in the reference case. This is what the final galaxy looks like in the largest case, so the case where the major merger is made the largest. And this is what the galaxy looks like when the merger is made the smallest. So here, the only thing we've really touched is how big or small a merger is at redshift 2. And you see this massive differences in the final galaxy structure at redshift 0, where we have a massive stellar disk and an almost elliptical quenched galaxy. And so we weren't all of this at the same stellar mass, and we weren't expecting this at all. Maybe we should have. Yeah, and then if you take the middle cases, you get something in between here, and then something slightly in between there. And so what seems to happen is that these changes in early history seem to leave really strong morphological differences at redshift 0 at fixed dynamical and stellar masses. And we are really in the process of trying to compare these scenarios with one another to really understand what is changing, whether it's something about the angular momentum accretion that stops the disk formation as a function of each scenario. And that will come when Oscar Agate will actually get to do it.
Can I ask something here?
Yes.
So I don't remember it fully, but it reminds me a little bit of Shai Janel's work from Flatiron, who showed, but I don't remember what parameters he tuned, but he showed like fine-tuning something very small in initial conditions in a cosmological zoom could completely change the outcome of the galaxy. So I'm just curious, do you think this is definitely just differences from the mergers, or could it also be just some random scatter that would always happen?
Mm-hmm. So what you're referring to here is amplification of noise and chaotic amplification of noise. And that's what Shai really showed. And this is something we've been very worried about. I can show you. So unfortunately, we can't do this simulation. The only real way to show that it's not is to run the same simulation 3 times or 5 times in a row. Unfortunately, we can't do this because these ones are too expensive. We have done this experiment previously on different sets of simulation, and we have done this with the dark matter only that I showed earlier. And what we usually see is that noise introduces differences in the final objects, but these differences are usually way smaller than what we introduce through the physical changes to the linear density field. I can't prove it with these ones because they are too expensive, but I can show you examples where we've tested it explicitly, and it's definitely something we're worried about. Okay, so for now...
The differences in M star was just incidental. The big difference we're supposed to be seeing is the structure. Is that right?
I think that's right, but it didn't have to be. Because when you do a cosmological simulation, you press play at redshift 100 or 1000, and then something comes out at redshift 0. You don't really control the final M star of the galaxy. So the fact that these are the same M star is also something that I didn't personally expect necessarily. And that we try to understand why in details. I have some preliminary plot I can show you later if you want on this. Okay, because for now, what I said I wanted to go into the Milky Way business a little bit. And so, as I've said, in the Milky Way, we actually have a lot of phase space information for the stars. So what we can do is to take one of these galaxies and extract the phase space structures of them. And so here I'm showing you the angular momentum in the z direction of the disk. So these stars have high prograde angular momentum. and this is the orbital energy of the stars. So inner stars are deeper in the potential well and have lower binding energies. And so if we populate this plot with all the stars from the simulation, you see towards the bottom, you have a pressure-supported little LZ component, which is the bulge. Then you have this sequence of high angular momentum prograde stars here that are the disk. And then at high energy, you have the stellar halo, who's also pressure-supported, but towards the outskirts, so much further out in the gravitational potential. And so if we extract the kinematics of the stars in the halo, just broadly defined as this box here, what we saw was this. And so here I'm showing you the azimuthal velocity, so where the stars are co-turning or counter-rotating with the disk stars as a function of their radial velocity. And the kind of spaceship-looking blob here that you see is the disk stars. They are turning at about 100 to 120 kilometers per second, which is about the rotational velocity of the disk. What's interesting is this radially biased component here, this component of heavily radial stars at low azimuthal velocity that link kinematically with the disk. And when I first made this plot, I was very excited because this is exactly what is seen in the Milky Way. This is an example from Ryan Naidoo and the H3 survey. So unfortunately, they use prograde as negative LZ, so you have to flip the plots in your head. But this types of highly radially biased sausage-looking stars is exactly what we see in the Milky Way. And so I was really, really excited when I first made this plot, because again, this is not something we anticipated. We started this whole radial merger idea in the fact that we might be able to reproduce something like this, and we actually did. But what came as even more of a surprise is when you repeat this plot across all the different scenarios, it's also there, it's also there, it's also there, and it's only really when you form an elliptical and you get rid of the disk component that you don't have this pattern of the radial stars overcoming the disk stars.
Oh, wait, can I ask, but didn't you say you actually set it up so that you would have a radial merger at redshift 2? So why were you surprised you saw this in the end?
Because we saw it in the case where this radial merger here is 1 in 40.
Okay.
So it's absolutely tiny compared to what we think happened in 1 in 14 stellar mass.
Cool, but you're also drawing the box right at the radial. I guess it was a pretty wide box, right? I'm just selecting the radial part of the diagram.
It is, but you still have a lot of contamination from the disk star. So it's just 0.5 LZ selection, which is kind of, it's not a very wide selection, but it's also not a very, very narrow selection. And also, would you have expected to see this pattern given how different the galaxy all look like?
Right.
So I'm still in the point where I don't fully understand this, but what seems to happen is all the scenarios have this radially biased of population that resemble the Gaia and Enceladus stars in the Milky Way, even when the radial mergers that we think produced it in the Milky Way is way, way, way smaller than the merger ratio inferred for the Milky Way, despite a massively different galaxy structure in each case, and all at fixed dynamical and stellar mass. And so I have some preliminary plot again on why that is, and the reason for this, and you're welcome to ask me if you want to learn more about it. Because they're not, as long as we take them with a grain of salt, because we haven't fully fleshed the analysis. Okay, so I'm probably getting quite close to the end, so that brings me to my conclusion, I think. So I hope I've convinced you that genetic modification is a great approach to construct control studies and to establish a causal account between a galaxy's past history and its final observables. By using it to scan through merger history, we directly probe the scatter in stellar halo content and structure at fixed stellar and dynamical mass. When we combine it with an efficient semi-numerical stellar halo modeling, it allows us to decouple how galaxy formation physics and merger history affect distinctly the expected diversity in the stellar halo population. Whereas when we combine it with hydrodynamical modeling, it enables detailed prediction of the kinematic signature of each of these merger scenarios while retaining a fully cosmological context. And I'll leave you with my summary and take any more questions that you might have.
Thanks a lot, Martin. Excellent talk. Should we first go to online? Because we had a lot of questions from people here. So I'm going to quickly ask if there's anyone online who wants to ask questions.
Yeah, I have a question.
Go ahead.
Hi, Ron. Thanks for the great talk. This is Kate Story-Fisher. I'm a grad student at NYU. I was really interested in your results that show the relationship between the merger history and the stellar density profile. And I'm curious if you might also see interesting phase-space structure and effects on the profiles in the dark matter halo, even if you don't have the hydro running, because we often run dark matter only simulations and then post-populate them with halos and with galaxies. And if you might be able to use the dark matter phase-space structure to inform things about the properties of the galaxies if you were to run the full hydro sims.
Yeah, so this is an excellent question. And the short answer is I don't have the answer yet, because I have a student working on exactly these questions and trying to extract the different phase-space structure, both in the stars and the dark matter, coming out of this study. So I can't answer that now, but I think it's a very exciting prospect.
Okay, cool. Thank you. I'm curious to see if that ends up being interesting.
Send me an email and I'll send you the draft when we have it.
Will do. Sounds good.
Sorry.
Yeah, also thought it was a great talk. And I know this is all preliminary, but I'm just curious what your thoughts are. Do you have any idea then if we maybe actually completely wrongly estimated the mass of the GSE, and what are your thoughts like comparing your different plots to the actual data plots?
So this is exactly why this is preliminary, and the reason why it is a bit difficult is because none of this galaxy is the Milky Way, right?
Mm-hmm.
They live in Milky Way mass halos, and they have a merger history that we think resembles that of the Milky Way, but none of them look exactly like the Milky Way, and so it's very difficult to link precisely to the Milky Way data.
Mm-hmm.
What I think is what we are uncovering here is that this types of signature and of radial signature might be way easier to produce in other ways than an accreted halo smashing through the proto-Milky Way. And what seems to happen, which is also something that was shown by Rob Grant with Auriga, is that at redshift 2 and 3, mergers are wet. And so there's an extensive component out of this radial stars that actually comes from the starburst that gets triggered by the interaction. And the starburst is larger with larger merger, but is still there even with really small accretion events. And so what I think we are seeing is that the stars that are, I can show you the actual plot because it's hard to. Okay, so this is, on the top is the star formation history of the radial stars. And what you see here are peaks corresponding to pericenter passage of different mergers, which made us think that this was starburst triggered populations. And here at the bottom is the metallicity distribution of these radial stars. And in blue is the starburst coming from the radial merger. And you see that in the case of the lowest mass ratio, this is the population that dominates the total very much, whereas as you go towards the right, you get this red population that is brought with the merger, the accreted population that starts dominating. And so what you're really seeing here is there's actually the radial population always exists, but there's a shift in its nature across the different scenarios, which I think is very exciting and might help not really directly interpret the Milky Way data, but rather contextualize it from this cosmological experiment.
I have a quick question. So that plot that you showed earlier, comparing the simulations to the observations, over 16 or so. So how much do you think of that, or what's the strength of the assumption of cold dark matter in that plot, do you think? What would the effect of a slightly warm dark matter model have?
Okay, so that's a good question. So is your thinking that with a slightly warmer dark matter model, you might suppress the formation of the smallest dwarf and reduce the amount of stellar mass? I think you would need, given the current constraints on both Milky Way satellites and Lyman alpha forest and so on, I think you already passed that point, because what contributes to the stellar halos are 10 to the 10 and 10 to the 11 solar masses halos, which are already not suppressed by the warmest allowed dark matter right now. I don't know if that makes sense.
Yeah, okay.
Let me make sure I got the sign of that. You're saying that warming up the dark matter wouldn't make a difference because the stuff that's doing the job anyway is not going to be suppressed.
Yeah, so I think what I'm saying is, in principle, it would, but in practice, we've already rolled out the part of the warm dark matter parameter space that would make a big difference. I think that's what I'm saying. I hope that makes sense.
Any more questions? Okay, let's thank Martin again. Thank you.
I don't see though, I think I didn't follow the last third very well.